Good morning, welcome to lecture 3 on partial differentiation. Right, it's been a little while since the last lecture, so let's just get started by doing a little bit of revision. So if the function f of xy, or that could be called z, is 4x squared y plus 12xy cos 4x plus 9. Then I want us to find partial df by dx and partial df by dy. Okay, remember these are partial derivatives, so when you're differentiating with respect to x, you treat y as if it's a constant, and if you differentiate with respect to y, you treat x as if it's a constant. So what I want you to do is pause the video there and have an attempt at it yourself. Okay, here's the answer. So let's look at partial df by dx to start with. So if we look at original function, this part here is got an x multiplied by y, so that's just something normal. So remember, we just treat that as if it's a constant. So you differentiate the x part, you give me 8x, and the y just stays the same because it's a constant, plus. Now, if we look at this bit here, that's a product rule because you get something with an x in it, 12xy, multiplied with something else with an x in it. So that's your 1, and that's your 2. So I'm going to have to do a product rule with that. Okay. Remember, your product rule is 1 dash 2 plus 1 2 dashed. Okay, so formula for the product is differentiate the first bit, leave the second part alone, plus you leave the first part alone and you differentiate the second part, right? So if I differentiate 12xy with respect to x, so I just differentiate the 12x part, so that just gives me 12, and the y part stays as it is because it's just a constant, so that's 12y. I leave that bit alone, so that gives me cos 4x, right? Plus, I leave the first bit alone, 12xy, and if I differentiate that second part, well, cos gives me negative sign, and the 4 comes out to the front because of the chain rule or the standard derivative, so that's times minus 4 sine 4x. And if I differentiate a number, I get 0. So I differentiated that first bit as normal, I used the product rule for the second bit, and that third term, 9, just becomes 0 when you differentiate it. Okay, so let's just tidy up everything. And that's the final answer that I get there for df by dx. Okay, and because that's a product rule, that would probably be worth 4 marks. Answer there. Right. Let's look at our original function again. So I'm going to write, because let's just call it part 1, right? I'm going to write down the original function again because I've put the product rule stuff around that, and I don't want to confuse it when I'm finding partial df by dy. And also I don't have enough room in my page. without having to move that paper up and down. Right. So I want to then differentiate this partially with respect to y. So partial df by dy. Right, so this bit here is just normal because there's no product. This bit here is just normal because there's no product. This bit here is just normal because there's no product. Right, so there's no product rule, quotient rule, anything like that. So all we're going to do is we're going to differentiate the y's and leave the x's as they are because they're constants. So if I differentiate that y, I would just get 1. So that means I'd get 4x squared. If I differentiate that y, I would get 1, so I just get 12x, and that bit's also a constant. So that's cos 4x plus. If I differentiate that 9, I just get 0. So partial df by dy is 4x squared plus 12x cos 4x, and that's me done. I could take a common factor of 4x from that bit there, but it's not going to really make it any more simple, so those would be my two answers. So I would say that's probably worth 4 marks, and that bit's worth 3 marks, or possibly even only 2 marks. Okay, so in higher maths and in the previous engineering maths we've done before, we have looked at finding maximum and minimum points on 2-dimensional surfaces or 2-dimensional curves. Now, because of partial differentiation and what we've seen so far, it deals with 3 dimensions. We are going to be able to work out maximum points, minimum points and saddle points on a 3-dimensional surface. So we can finally deal with 3D surfaces, and really useful in certain types of design engineering, more mechanical than electrical engineering, but it's really important. So this is called finding maxima, minima and saddle points on 3D surfaces. Right, so to find where stationary points occur, we have to make partial df by dx and partial df by dy equal to 0. Nope. Alright, that would make sense. So to find where stationary points occur, we have to make both df, partial df by dx and partial df by dy equal to 0. Now, then have to factorize and or use simultaneous equations. To find all of the stationary points now. We've done enough mathematical or done enough mathematics in this course now, So you should be able to identify where you've got to factorise or where you've got to use simultaneous equations. You will see as we go on when you're going to use each point, or when you're going to use each type of or when you're going to use each of these to actually solve for stationary points, right? So just like when you find the stationary points on a two-dimensional curve, you have to use the second derivatives to work out whether they are maximum, minimum, minima, or saddle points, right? So let's have a look at minima. Right, so that's when you've got this kind of, within a curve, you've got a bowl shape. It looks like an upside down kind of bowl or valley. And they describe that as being pudding bowl shaped. Right, and this happens when either partial df squared by dx squared or partial df squared by dy squared is more than 0. So that means when it's a positive number. But that's pretty much as difficult as it would be making one choice if you were doing two-dimensional. But what you've also got to look at is that in order for that to happen, d squared f by dx squared multiplied by partial d squared f by dy squared, take away partial d squared f by dx dy squared is greater than 0. Okay, so you've got these two things that need to happen in order for me to get a minimum. But you'll see it through example later on. So both these things have to be positive. All this means is I multiply the second derivative with respect to x with the second derivative with respect to y, and I subtract the mixed derivative squared. And it's got to be greater than 0. Okay, local maxima. Right, and that's kind of the opposite. They describe that as being like a molehill. And this happens when either d squared f by dx squared or d squared f by dy squared is less than 0. So a negative number. And you've also got the second property, So the local maxima happens when either the second partial derivative with respect to x or the second partial derivative with respect to y is a negative number, and also your two normal second order partial derivatives multiplied together take away the mixed partial derivative squared is more than 0. Right? And then the last one is the saddle point. Now, it's really, really, really difficult for me to draw maxima, minima and saddle points of a 3D surface on a bit of paper, especially when I've got no technology here. I've just got paper and pen, and my drawing's not amazing, as you know. So if you Google it and have a look at maxima, minima and saddle points in three-dimensional surfaces, you'll have a far better understanding of what's going on. So, and these happen when d squared f by dx squared multiplied by d squared f by dy squared take away your mixed derivative squared is less than 0. So we have 3 cases. Right, now I'm going to go through this 2 or 3 examples on this, and then I'm going to get you to look at some from the book, partial derivatives. So let's have a look at the first example. Example 1. Find stationary points Okay, so find the stationary points on the surface f of xy equals x cubed take away 15x squared take away 20y squared plus 5, and describe their nature. Okay. Look at the answer. So first thing we're going to do is we're going to differentiate with respect to x and differentiate with respect to y. So df by dx, remember we're differentiating partially, so you're differentiating all the x's and treating y's as if they're constants. So if I differentiate that, get 3x squared. If I differentiate that, get 30x. Now there's no x in that term, so that's a 0, and there's no x in that term, so that's 0. So partial df by dx is just 3x squared take away 30x. Right, now what you should always try and do is see if there's something you can do to the first derivative, right? So you need to say for stationary points df by dx and df by dy are equal to 0. So that allows me to put 0 here, like that. And then, as I say, try and factorise if you can, right? So CDT, look for common factors, look for difference of two squares, look for so factorise if possible. So that's common factor, difference of two squares, and trinomial. So I can factorise that part there. They're both in the 3 times table, and I've got x. So that's a common factor. And then inside the bracket, 3x multiplied by x would give me 3x squared, and 3x multiplied by 10 would give me 30x. So remember, when you've got something that's factorised and it's equal to 0, we just split it into 2 bits. So that means that 3x is equal to 0, and x take away 10 equals 0. So x is 0 divided by 3. So x is just 0, and x is 0 plus 10. So x equals 10. So those are 2 x values. That I've got of my turning point. So you differentiate it, you set it equal to 0 because, and state this important thing here, because otherwise you're not really telling a story, you're just following a process. So you need to state the story as it's happening, and then you factorise and you find your 2 values. Right, next, so I've found partial df by dx, but I've also got this for stationary points partial df by dy is equal to 0, and for a stationary point you need both x and y. Right, so I'm going to write down my original formula again, just because you're not going to be able to see it. You guys obviously don't need to do that because you can look up your bit of paper. Right, so I'm going to find partial df by dy. So differentiate that. Well, that's not got a y in it, so that's 0. That's not got a y in it, so it's 0. Differentiate that, I get 40y, and differentiate that, and I get 0. So all these terms are 0 because they don't contain a y. So partial df by dy is just negative 40y. Okay, but we know from for stationary points to happen, df by dy must be equal to 0. So that means I swap my df by dy for 0. So 0 equals negative 40y. So y equals 0 divided by negative 40. So that tells me that y is equal to 0. Right, so I've got my original function. I've partially differentiated it with respect to y, which has given me that the partial derivative with respect to y is negative 40x. Now I know that at my stationary points, df by dy, or partial df by dy is equal to 0. So I want to work out what y is. So all I've done is I've moved the 40 over, which makes it a divide, and that means that y is equal to 0. So what that tells me is that at my stationary points, is only ever 0. And my stationary point values for x is 0 and 10. So, because we've got 2 x values, I need to have 2 stationary points. Remember, stationary points are coordinate points. Right, so my 2 values of x are 0 and 10. And the only value for y that I've got is 0. So that means that they both must happen at 0. Right, so let's crack on and work out their nature. So we want to know if they're maxima, minima, or saddle points. Maximum, minimum, or points of inflection would be the equivalent in 2 dimensions. Right, so what I need to do is I need to find all the second derivatives. Right, so we're looking to find the nature. Right, so I'm going to write down all my first derivatives that I got from the start. The first derivative with respect to x I worked out before, was 3x squared is equal to 30x. I got that from the first part. And the first derivative with respect to y that I calculated in the first part was negative 40y. Yeah, it was my first derivative with respect to x. And there was my first derivative with respect to y. So I've already worked those 2 things out. Now what I need to do is I need to differentiate that with respect to x again, that with respect to y again, and I also need to find the mixed derivative. Right? So let's differentiate this with respect to x again. So if I differentiate that with respect to x, get 6x, differentiate that, well that's just becomes negative 30. If I differentiate that with respect to y again, I would just get negative 40. Right, now I need to find the mixed derivative, and the mixed derivative that I always tend to use in this is d squared f by dx dy. And remember, that's the one you do first, and that's the one you do last. Right, so what I'm doing is I'm taking this, so I'm finding that partial derivative, because that's what it tells me is the partial derivative I need to look at to confirm the nature of my maxima, minima or saddle points. So you take that and you differentiate with respect to x. That's what that means. You take the first derivative with respect to y and you differentiate that with respect to x. Right, so I'm taking that and differentiating that with respect to x. Well, there's no x in it, which becomes 0. So I've now got the 3 things I need to make my decision. Right, so I've got my 3 derivatives here. Now, the easiest way to do this is to draw a table. It would be nice if you could use a ruler, but as I'm in my flat and I don't have access to anything, I don't have a ruler at the moment, it's down in the car, so I'll just do it freehand. Right, so you're going to put in your table some headings. So here is your turning point at your stationary point. In fact, I'll call it stationary point because that's what we've been calling it. Stationary point. Then d squared f dx squared, d squared f by dy squared, d squared f by dx squared multiplied by d squared f by dy squared, take away d squared f by dx dy squared, and then nature. So it would look a lot better if we had a ruler, but hey. Right, so first thing I do is I put these two stationary points that I've got into my table. So my stationary points were 0, 0, and 10, 0. Right, now first thing is remembering your stationary points. That's your x and that's your y. That's your x and that's your y. Right, just as a little reminder. So what we do is we substitute our x and our y value into the derivatives. Right. So in this derivative here, this is my second derivative, right, d squared f by dx squared. And what I'm doing is I'm substituting my x value in. At this first stationary point, x is 0. So if x is 0, that there is negative 30. Right, same in this one. This here, I'm substituting in anything, well, I don't have to substitute anything in. It already tells me that the second derivative with respect to y is negative 40. So that's all good. So if it's just a number, you just put it into the table. If it's got a letter in it, you substitute in the letters from your the value of the letters from your stationary point. Right now, I've got to use this formula. So partial df squared by dx squared is negative 30. This bit here is negative 40. I'm subtracting 0 squared. And if I work that out, that gives me 1200. Okay, so let's have a look at my three possible cases. Right, so what I've got is I've got that this horrible long bit, d squared f, the second derivative with respect to x, multiply the second derivative with respect to y, take away the mixed derivative squared is greater than 0. Right, and I can tell that's greater than 0 because that's 1200 in this case, right? And that big horrible thing there tells me that because that's greater than 0, it's either a maximum or a maxima or a minimum. Because for a saddle point, that thing there is less than 0. Right, now what I need to do is look at the single derivatives, these derivatives here. So if I look at them, they are both less than 0. So if they're less than 0 and that's more than 0, it tells me it's a maxima. So that's a max. Right, let's do the same for the next one. So I've got my stationary point 10, 0. So that means I go to the second derivative with respect to x and I substitute in 10 in its place. So that will be 6 times 10 is 60, take away 30 means that for this bit here I've got 30. Right. The second derivative with respect to y, that's just negative 40. There's no letters to substitute in for that one. So negative 40. Right. So I'm going to substitute in these values. That's 30 multiplied by negative 40, take away 0 squared, because my mixed derivative is 0, and that's my formula, and that gives me negative 1200. Right, so this time my long horrible formula involving my mixed derivative is less than 0. So let's go to my 3 cases and see what happens when that's a negative or less than 0. So if I go to my 3 cases, if I look at my minima, it's not a minimum or a minima because that's greater than 0. It's not a maxima because that's greater than 0. But it is a saddle point because that happens when it's less than 0. So this, if this is less than 0, you can tell straight away that that's a saddle point. So 0, 0 is a local maximum, and 10, 0 is a saddle point. Right, so that's me done the first example, and as you can see it's quite long-winded, it's quite a lot of work, but hopefully you can see where it's all coming from. So I'm going to do a second example now. Okay, so I've just shortened the terminology there. So find the stationary points and describe their nature. That's what I'm going to do here. So slightly different function. Again, rather than being f of x, y, they could call it z, and it would be exactly the same thing. So f of x, y is 4 plus x cubed plus y cubed, take away 3xy. Now if you want, you can stop the videos here and try it yourself, but otherwise I'm going to continue with the answer. Right, so first thing we're going to do is find the, I'll draw a wee line. First thing I'm going to do is find the partial derivative. So df by dx. So I differentiate that, it's going to be 0. Differentiate that, dx squared. That there doesn't have an x in it, so it's just going to become 0. That x is just going to become 1. So that just becomes 3y. Right, so remember with partial derivatives, if it doesn't have this letter in it, then it just becomes 0 because the terms are constant. So that's just a number, that value y is just a number, so you differentiate, it becomes 0. You differentiate that x, it becomes 1, so you're just left with 3y as your derivative. Right, so let's just simplify that. Right, so that's me done that. Now, what I then look and try and do is I then say stationary points when partial df by dx, partial df by dy are equal to 0. So that's a statement, or turn-in points, or whatever you want to call them, but that's a statement that needs to go in every answer, just like it needed to go in the higher maths. Right, now, what I then try and do is, I try and factorise meaningfully. Right, the only thing I can do is take a factor of 3 out of it. So, the factorising, that isn't going to help, so sorry, 0 equals 3x squared take away 3y. Should be that, I'm trying to factorise, but it's the same thing. This is not equal to 0, sorry. Right, so I can't factorise that meaningfully, right? The only common factor in there is 3, and that's not going to help me with anything, so I'm just going to leave that the way it is. Right, so I can't do anything yet if I can't factorise it meaningfully, right? And by meaningfully I mean there's a letter common factor in there. Right, so then I'm going to differentiate it with respect to y. So if I differentiate that with respect to y, I get 0. Differentiate that with respect to y, I get 0. Differentiate that with respect to y, I get 3y squared. Differentiate that with respect to y, well that just becomes 1. So it becomes negative 3x. So differentiate that, it's a number, so it becomes 0. Differentiate that, it doesn't have a y in it, so it just becomes 0. Differentiate that with respect to y, you get 3y squared. This does have a y in it, so you differentiate the y, and I'm just left with 3x. So simplify that. Right, so again, 0 equals 3y squared, take away 3x. Right. So that means I've been left with two equations, and again I could try and factorise that, but I can't do that meaningfully either. I can't get a letter common factor or do a trinomial or anything with that. So I said again you could take out the 3, but the 3 is not going to help us there at the moment. Right, so you've got two equations, right? I'm just going to write them out the other way around. So 3x squared take away 3y is equal to 0. And you've also got the equation 3y squared take away 3x is equal to 0. Okay, now these are both in the 3 times table. So you could write that as Okay. These are also both in the 3 times table. So you can just divide everything by 3 because it's equal to 0. Right, so that tells me that I can say that x squared equals y. Okay. So if x squared is equal to y, that means I can put this x squared into this equation in place of y. So that means that x squared squared subtract x is equal to 0. So I'm doing simultaneous equations. So x to the power of 4 take away x is equal to 0. And now I can take out a meaningful common factor. x cubed take away 1 is equal to 0 because x appears in both of these terms. So that's equation 1. That's equation 2. So I've simplified equation 1, so I've got it as being y is equal to something. I've then substituted that value I've got for y in place of y in the second equation and factorised. So that means that x equals 0 or x cubed take away 1 equals 0. So x cubed equals 1, so x cube root of 1, which means x equals right. So let me just talk you through that before we go on to the next bit. So we couldn't factorise it meaningful at the start because there was no common factor. Now I got 2 equations, one which I got from df by dx, and one that I got from df by dy. Now you've got to, if you can't factorise it, make it so it's either y equals something or x equals something. So I got this equation to be y equal to something. Then what I did is I substituted that in place of the y in the other equation, so it meant an equation with only x's in it. That then allows me to factorise and then split it into 2 strands, so I get 2 values for x. Now, I need to work out my y coordinates. But here, x squared is equal to y, so y is just x squared. Right, if you write that the other way around. So that means that for this value here, when x equals 0, y equals 0, because 0 squared is equal to 0, that gives me 0, 0. When x equals 1, y equals, well, x squared, so 1 squared which is just 1. So those are my turning points, or my stationary point, 0, 0 and 1, 1. So it's simultaneous equations. Right, so then to find the nature, so again, first thing you do is you write down the first derivatives that you had already calculated. And you differentiate them again. So differentiate this one with respect to x again, and that gives me 6x. Differentiate this one, keep on forgetting to put that wee 2 in, make sure you put that squared in. And if you differentiate this with respect to y again, you just get 6y. Now, finally, you need to find the mixed derivative, so that's d squared f by dx dy. So it's this one here, and differentiate with respect to x. So if I differentiate that with respect to x, I get 0. Differentiate that with respect to x, I just get negative 3. So it's negative 3. So those are the three second derivatives that I'm going to put into my big table. Right, so my table stationary points, d squared f by dx squared, d squared f by dy squared, d squared f by dx squared, d squared f by dy squared, take away d squared f by dx dy squared, and nature. Right, so I'll put in my turning points, my stationary points. So my stationary points are 0, 0 and 1, 1. Right, so d squared f by dx squared is 6x. So that's my x value of the turning point. Y, x, y. So if I put 0 in place of that, I just get 6 times 0, which is 0. Right, here, d squared f by dy squared is 6y, but my y value is 0, so if I put 0 in there, I just get 0. Not looking great so far. So then we put our number into that, so it's 0 times 0, take away, and my mixed derivative is negative 3 squared. Right, so 0 multiplied by 0 is 0, negative 3 squared is 9, so that's 0 take away 9, which is negative 9. Now if I go to my 3 possible cases, if this long thing here is less than 0, automatically it tells me that it's a saddle point. Right, I then substitute these values into these two derivatives. So if I substitute that into there, I get 6. Substitute that into there, I get 6. 6 multiplied by 6, take away negative 3 squared. So 6 multiplied by 6 is 36, take away 9 is 27. So I do have to make a choice this time. So is it, I know that's greater than 0, so as soon as that's greater than 0, I've got, is it a maximum or a minimum? So I've got to make the decision, is it a maximum, is it a minimum, or is it a saddle point? So let's go to a maximum or minimum, because it is one of them. So maximum or minimum, right, so that bit's right, and that bit's right, so I then need to go back into the table and look at these bits, this bit here, right, so they're both positive. So that one of them has to be negative for it to be a maximum, but if they're positive it makes it a minimum, so that means that's a min. So that means it's 0, 0 is a saddle point, and 1, 1 is a local. Minimum. Right, now what I would like you guys to try, and I know these questions are tricky, right, they are tricky, but if you want, I will, if I've got time, put answers up to whatever ones you find the most difficult. So if you can look at worksheet 4, on page 35 of your partial derivatives booklet. Put the questions in front of the camera just now so you don't necessarily. Right now, 5 is much too difficult. So I would look at trying to get 1 to 3 done. Now these are going to take you a while, but please let me know the ones you struggle with, and I will endeavour to put the answers in video form if I can. Now these videos take a long time to process, so it might just be the case that I take some pictures of handwritten solutions and put them up. Right, it depends how much time I've got left. So if you let me know if it's 1, 2 or 3 you're struggling with, maybe it's 2 and 3, maybe it's 1 and 3, remember the answers to those questions are at the back of the booklet, and all those booklets are on Microsoft Teams. Now I'm only doing one lecture this week because I've also given you that assignment to do. That assignment is due in next Friday. Now it is not the same as the exam. It is different. There are different questions. Some are slightly more difficult, some are slightly easier. Right, so do not think that that assignment is the exam. That assignment will give me some evidence to show that you would have been capable of passing the exam, but it is not the exam. Okay, it's just an assignment so I can use it as evidence at this difficult time. Okay, enjoy the rest of your week.